Okay, so hi everybody, welcome back to this seminars in University of Thessaloniki in a virtual form. And today we are very happy to have Eleni-Alexandra Kontou with us talking about singularity theorems in semiclassical gravity. Eleni is currently a postdoc in the University of Amsterdam. And so Eleni, you are ready to start.
Thank you. So today I'm going to talk about singularity theorems in semiclassical gravity, and this is kind of an overview of the work I've done the past few years with various collaborators, mainly Chris Fuster, Jackson Fleece, Ben Freibagel, and Dimitris Kromidas. Sorry, this is the slide. Okay. So the talk is mainly based on these three papers from geodesics and for null geodesics, as they have slightly different issues. So let's start with some very basic things. What we mean by a singularity in general relativity. So if you've taken an introductory GR course, we usually talk about a place where the curvature diverges. So we calculate the curvature scalars, maybe in Schwarzschild, and see that at R goes to 0, they go to infinity. So this is the singularity in that context. Now, this definition has two problems. The first problem is the word place, and that's why I put it in quotes, because except in highly symmetrical cases like Schwarzschild, we cannot represent the singularity. So in Schwarzschild, the singularity is represented as a boundary, but this is not always possible. So the metric is not defined where we have the singularity, so we generally cannot talk about a place. The second problem is that the divergence of curvature scalars does not cover all singularity cases. So one simple example is, let's say we have Minkowski space, and we cut part of the space-time and we connect it to make a cone. And then the tip of the cone is a singularity, but the curvature scalars are everywhere 0 because it's still Minkowski space. There's no intrinsic curvature. So this case is not covered by the divergence of curvature scalars. So what is a better definition, and the one that we usually use in GR, is that a space-time is singular is if it has at least one incomplete geodesic. So instead of looking specifically at the strength of this definition is generality, is also kind of its weakness. So if we prove a singularity using this definition, we actually don't know if the curvature or the energy density or something else diverges at that point. We just know that the geodesic ends. But this is the definition we use in singularity theorems, and this is the definition that I'm going to use for this talk.
What do you mean incomplete?
I mean that they end and they're inextendable. So you cannot extend the geodesic further than a specific point.
Okay.
Okay. So next I will talk about the singularity theorem structure, because pretty much all singularity theorems have a very similar structure from the original theorems of Hawking and Penrose. And this is basically having three conditions. The first is the initial or boundary condition. And this is the existence of a trapped surface. Well, the null normal is always negative for null geodesic, or a special slice with negative expansion for time-like geodesic. To understand a little bit what that means, I'm going to give two examples. For the null geodesic, have the example of the Schwarzschild geometry. So this is in Eddington-Finkelstein coordinates, and the blue lines represent the ingoing null geodesics. So as we expect, the ingoing null geodesics go from some point in space into the black hole and end up at r equals 0. The strange thing is what happens with the outgoing null geodesics, the red ones. So outside of the classical horizon, it's Schwarzschild and then the light going back in. But this strong condition is the trapped surface. For the time-like case, we have a spatial slice with negative expansion, and this is, for example, what happens in cosmology. So if we take a constant time slice in a cosmological, let's say FRW space-time, and then because of the expansion of the universe, if we look in the past, then we have negative expansion. So this also satisfies that initial condition for the singularity theorem. The second condition, which is the one I'm most interested in, is the energy condition. Energy conditions generally express restrictions on the stress energy tensor. And we usually say they express physical properties of matter. We'll see how physical these properties is. The original singularity theorems used the null energy condition for the null geodesic and the strong energy condition for the time-like geodesics. So what we call the physical form of the energy conditions is they're expressed as contractions of the stress energy tensor. So the null energy condition is the stress tensor contracted with two null vectors. And the requirement is that this quantity is everywhere non-negative. Similarly, for the strong energy condition, we have contraction with time-like vectors u. The expression is a little more complicated here. T is the trace of the stress tensor, and n is the number of space-time dimensions. However, if we use the Einstein equations, both conditions look quite similar in what we call the geometric form. The geometric form we sometimes call the null convergence condition and the time-like convergence condition, respectively. And these are conditions on the Ricci tensor. So the geometric form is the one that appears in the singularity theorem. To understand the physical meaning of the energy condition, we can use a perfect fluid stress energy tensor. So for the null energy condition, we have the requirement that the energy density and the pressures everywhere are non-negative. For the strong energy condition, the interpretation is less straightforward because we also have this little strange condition that has also to do with the number of space-time dimensions. For classical fields, maybe the null energy condition seems reasonable. The strong energy condition, maybe not so much. So it's already pretty clear that maybe these conditions are not expressing exactly physical properties of matter. The third condition is the causality condition, and that is the existence of a Cauchy surface. A Cauchy surface is a space-like hypersurface which intersects causal geodesic only once. So I'm not going to present a proof of a singularity theorem, but just to give you an idea of how they work, we can think about having a congruence of geodesics, and the initial condition, the trapped surface or the negative expansion, means that the geodesics start focusing. The energy condition guarantees that the focusing continues, that there's not any kind of matter that allows the geodesic to defocus. And third, the causality condition is telling you that there are no focal points. So the first two conditions lead to the formation of a focal point, but the third condition contradicts that and tells us that there could not be any focal points. So that contradiction leads to geodesic incompleteness. Since there can't be any focal point, then the geodesic must end. Work. Now, I already talked a little bit about the energy conditions and their problems. The pointwise energy condition are violated by some classical, specifically the strong energy condition is very easily violated even by classical fields. And more importantly, these conditions are violated by all quantum fields. So quantum fields can admit negative energies. There's always some state that it has negative energy. So we can't hope to have any semi-classical singularity theorem, any singularity theorem that is applicable for quantum fields if we keep these pointwise energy conditions. So we need some weaker condition. So the first question is, can we have singularity theorem with weaker conditions? Specifically, the condition I will focus on is where we're integrating the Ricci tensor contracted with some time-like or null vectors smeared over some geodesic. And then we also have a smearing function f. So then the requirement is that this quantity, like on average, is larger than a negative bound, which we'll see what it depends on. So that's a sort of an average condition. So it's a much weaker condition than the previous pointwise ones, because these ones required the energy density or similar quantities to be non-negative at every space-time point. And the next question is, can we have semi-classical singularity theorem? So these questions are slightly different because we not only have to prove the singularity theorem for the weaker condition, but we also have to show that the quantum field obeys that energy condition. So I will talk these questions here. So for the singularity theorems with weakened energy conditions, there have been various efforts for that. There have been various proofs for conditions of that form. I'm going to talk and use our own theorem that proved with Chris Fuchser a few years ago. So the energy condition here is on the left, we have the quantity that I showed you. So for the time-like case, it's the Ricci tensor contracted with time-like vectors and some smearing function f. And the bound here depends on that smearing function. And in particular, the L2 norm of the smearing function and the mth derivative of the smearing function, the L2 norm of that. So here, the Qm and the Q0 are just positive constants. We don't know what they are yet. So this is just a bound and they're just positive finite constants. In addition to this very weak condition, we require either the strong energy condition to be obeyed for a short time after we measure the initial contraction, so for time, tau naught, or that the strong energy condition is violated before we measure the initial contraction. So again, for some time minus tau naught before the 0 point, which is the point of our Cauchy surface. The initial condition is also modified, and that makes sense. We have a weaker energy condition. We need to have a stronger initial condition. So for the original Hawking theorem, we had the initial contraction to just be negative. So K has to be less than 0 in the Hawking theorem. Nu, and that number depends on the constants that come from the energy conditions, Qm and Q0. It also depends on the time that a strong energy condition is obeyed or violated, tau naught, and it also depends on the time of formation of the singularity tau. The causality condition is the same, and it's the existence of a Cauchy surface. So this theorem works exactly the same way as the original singularity theorems. So we have the initial condition that is a stronger condition now, and then the energy condition allows for some negativity, but not enough to actually defocus the geodesics. And the result of the space-time is time-like geodesically incomplete. And in particular, the singularity is before proper time tau.
This slide, what is n and how is it determined? It has to be just some positive integer, or?
So here at this point, m is just an integer. So we don't specify it. We're going to see that if we have a theorem, we can derive this condition for that theory and actually find what is this M and what are these constants. But at this point, it's just a general condition. So with this kind of condition, we can prove the theorem.
Okay, thanks.
We have a very, very similar theorem for null geodesics. So it has exactly the same form. Instead of the initial contraction, we have the mean normal curvature H. Here, just because we have null geodesics, we need to fix a parameterization of the affine parameter lambda. The affine parameter. But otherwise, the theorem is very, very similar for null geodesics. All right, so we have the theorem for weekend conditions. And now how do we go from there to semi-classical singularity theorems? The first step is to actually prove energy conditions for quantum fields. And these conditions are called quantum energy inequalities. So here is an example of a quantum energy inequality. It's a bound of energy density in Minkowski space, one of the first quantum inequalities that was proven. So here we have the stress tensor contracted with two time-like vectors, and this is a quantum object now. So we need to renormalize it and take it at some quantum state omega, and then smear over a time-like geodesic with a smearing function f. And now the bound, you see that it's sort of in the form of the bound that I showed you before. So here we have two derivatives on the smearing function, and we take the LT norm of that smearing function. So this bound is it's exactly in the form that I showed you. The second step is to move from quantum inequalities to geometric conditions. So I already told you that for singularity theorems, we actually don't have bounds on the stress tensor, but we have bounds on the Ricci tensor. So for classical fields, we use the Einstein equation. For a quantum field, we use the semi-classical Einstein equation. So the way we use it is very simple. We have a condition on the stress tensor, the expectation value on the stress tensor, and then we connect that to classical curvature. And so we have a condition for classical curvature. The third step is to actually estimate the required initial contraction or mean normal curvature for physical spacetimes. So to give an example, to see if the theorem that we can prove for some quantum field is actually applicable. Because if we have a very, very strong initial condition that is never satisfied, then the theorem is not very good. It has no applicability. So I'm going to talk about how to do these three things for time-like geodesics and for null geodesics. Are there any questions? All right. So let's start with time-like geodesics and the quantum energy inequality. So the quantum energy inequality that I'm going to use is a difference one. So what do I mean by that? I mean that we take the expectation value of energy density or similar quantities. We see what's the quantity of interest here at some state omega, which is the state of interest, and subtract the expectation value at some reference state. Now, the important thing is that this difference is actually smooth, because the class of states that we pick, they're called Hadamard states, have a known singularity structure. So as you know, when we have the 2-point function of a quantum field, or the stress energy tensor that includes squares of the field, it actually diverges in quantum field theory. So we need to somehow get rid of those singularities. So here we take the difference of two states that have the same singularity structure, so the singularities are subtracted. Now, this bound in the very, very general case can actually depend on everything. It can depend on the state of interest, on the reference state, and on the smearing function. So the most general case is that the bound has a dependence on everything. So what is the observable of interest here? It is what we call the effective energy density. So this is the little strange quantity that appeared in the strong energy condition, if you remember from one of my first slides. And it's the quantity that we need for the time like the Hawking singularity theorem. And what theory are we taking? We're taking the minimally coupled scalar field, which is one of the simplest fields we can take. So what we do is we take the minimally coupled scalar. Here, capital M is the mass, and we quantize it and derive this difference quantum inequality for the effective energy density. And this is the result. So on the left-hand side, we have this difference between the two states, the state of interest and the reference state for the effective energy density, the quantity that appears in the strong energy condition. And on the right-hand side, we have the bound. So let's see what's going on with this bound, because it doesn't yet look at all like the bound that I had for the singularity theorem. So the first term is the term that depends on the reference state. So this W0 is a 2-point function of the reference state. And form of that. The important thing is that we have shown that this term is actually finite, the integral converges. The second term depends on the mass of the field, and it also depends on the weak square of the state of interest. So this is what we call a state-dependent quantum inequality. There's also dependence for the state of interest, which is not an ideal case. It would be better if we didn't have any dependence on the state of interest. However, it is a non-trivial bound in the sense that we have no derivatives in the term that has the dependence on the reference state. So it is still an interesting bound. It's not in the form that we wanted yet, but it is a non-trivial bound.
Eleni, can I interrupt you? Thanks.
Yes.
So on this term precisely, in the massless limit, the only change is that this term goes away.
Yes.
Okay, so you get stronger inequalities, stronger constraints in some sense.
Yes, in this case, the massless case is actually easier.
Okay, thanks.
And we can also see that classically. So for the classical strong energy condition, the massless scalar obeys that condition, but massive scalar doesn't. So it actually comes from that. So there are two problems with this inequality. The one is that it has dependence on the state of interest, which I'm going to talk a little later, and the other is that it also has this dependence of the first term on the reference state. And as we know, when we're talking about quantum fields in curved space-time, it's generally very difficult, or in some cases impossible, to find actual expressions for some reference state. So what we did here is to use basically the equivalence principle for the space-time. For tensor functions that have sufficiently small support, the bound continues to hold. For the W0, the 2-point function of the Minkowski vacuum. So the idea is that we always can find a function with sufficiently small support to actually approximate Minkowski space, and for our reference state to be able to be close to the Minkowski vacuum. And for the Minkowski vacuum, we know what is the 2-point function.
May I ask a question, if you don't mind? I'm getting back a little bit, if you can, a couple of transparencies to see whether I can get the idea. When here, yes.
Here?
So yeah, in the top equation, Well, you have the expectation value of rho, which is, I suppose, an energy. Well, it could be the energy density of this energy momentum tensor, for example. Now, I'm interested about what you call the state of interest. Can this be a thermal state?
Yes, it could be.
So that, well, the reason I'm asking is because this difference that you have, that you say it kills the singularities, is what people do sometimes in thermal field theory when they subtract the zero temperature expectation value of some quantity. And I will give you a concrete expectation value of the energy momentum tensor, of the trace of the energy momentum tensor in a thermal state. I'm asking this question because later you mentioned that there is a problem in calculating this kind of quantities in curved space-time. And so I was wondering whether you thought or anybody else has thought of calculating this kind of quantities in a curved space-time, which is the thermal geometry, which is like a cylinder, which actually has non-trivial expectation values, gives non-trivial expectation values, various quantities. So I just want to point out that there are many interesting results of this kind of quantities, which whether you can comment on that, whether they can be useful in calculating, verifying this kind of bounds.
Yeah, so we have an example. It is in Minkowski space that we did the KMS states, thermal states. So we have calculated this bound for these kinds of states. We haven't looked at thermal states in curved space-times. I'm sure there are some examples, but which could be interesting results. But again, you would have to kind of specify the geometry to be able to have these particular states. And the idea here is to keep the geometry of space-time as general as possible. And in very
yes, sure, but where does the geometry of space-time enter in this first line here?
Oh, it's just here. It's just about the what states you can choose. Yes. So if you have a particular geometry, then you can pick also some kind of states. So that's the only way it enters here. Mm-hmm. And of course, yeah, of course, then it enters in the bound in that form, because the bound can depend on the state.
Okay, thank you. Yes, maybe we will discuss this later because it's becoming interesting to me.
So our technique was to find a function of small support in order to pick the Minkowski vacuum as our reference state. And our first thought was maybe we can break the geodesic into very small parts, in equal parts, and have this function of small support at every point in the geodesic. But that proved to give a not very good bound. And the reason is, if we think about cosmology, the curvature increases in the past, and maybe close to the singularity, we can have very large curvature. So if we have a constant support of the function and we break the geodesic into equal parts, then this support has to be very, very small in order to be valid even close to the singularity. However, if we have a varying support of the function, that could allow us to have a larger support closer to our time. Let's that turned out to give a better bound. So what I'm going to do is consider functions of varying support with some function t. So we use the 2-point function of Minkowski vacuum and assume that every piece TT of the geodesic, we can apply the Minkowski inequality. And with these two, we have the following inequality. So the first term, you see now it's explicit. We are able to calculate it by using the Minkowski 2-point function. The second term remains as it is. And this inequality is valid for all those functions of small support. So from t minus tt over 2 to t plus tt over 2 until the end of the integral at a proper time tau. And this is valid for overall Hadamard states omega. And an additional assumption we made is that the space-time is even. And now, at this case, we know what M is. And M is half the number of space-time dimensions. So for 4 dimensions, this M is equal to 2. This S here is the area of the 2M minus 2 sphere. So the next step is to use the semiclassical Einstein equation, or SEE, to move from that bound to a bound on the curvature. So as I said, this happens immediately. We don't actually look for solutions. This is a different and quite hard problem to look for solutions of the semiclassical Einstein equation, but we just assume that there is such a solution that our quantum inequality holds. The next step is to deal with this state-dependent part. So as I said, it's not very good that we have this state dependence. However, it also does not have any derivatives on the field. So this is just the weak square of the field for the state of interest. And so what we do is we assume that there is a class of states where the weak square of the field for this class of states is bounded. And there is some maximum value of the field phi max squared. This is certainly a weak point of the inequality that we need to assume that. But there are actually classes of states that they do have that property. So for what we call the phi max solution, the solution for states that the field value is bounded, and we have the T-regular geodesics, the geodesics that were broken into these parts, we have this energy condition. And that energy condition is exactly in the same form that we had from the theorem. So for this energy condition, we could apply the theorem. But this is still an energy condition that is for a function of small support. So this energy condition holds for functions f that have support tt, have a small support. So we don't want that for the singularity theorem. We want functions, test functions that have a large support over the entire geodesic. So what we do, we break the geodesic into the n pieces, each of supports t of t, and then sum the resulting inequalities. So we have these smooth compactly supported functions that they span the entire geodesic, and each of them has the supports t. What are the QMs and the Q naughts? So the QM has a very simple dependence on just the space-time dimensions, while the Q naught depends on the field. So it depends on the mass of the field, and it depends on the phi max, maximum value of the field. And we still have to deal with this term here, which has the m derivatives of the function. So to do that, we have to, at this point, pick a particular t of t, that's the support of each function. We just pick a simple linear function that decreases, and then we also pick a specific phi n. So the phi n is a pretty complicated function, but I think it's better to show how it looks. So this is a function that goes smoothly up to 1, the phi n, and then goes down in a sharper way so that the support decreases as we go to time tau. So we start with a larger support, we go to a smaller support. And these are all functions that are compactly supported and have maximum value of 1. And with these choices, we can actually bound this term and have it to be a sum of coefficients that depend on 2 parameters. The one is the capital T naught. So this is the support of the function at time equals 0. So this is the largest support that the function can have. And tau, which is the time of the singularity. And that I'm going to symbolize with the triple lines of the Sobolev norm. And it has the form of the theorem that we had before. And we know exactly what the QM and the Q naught are. Remember, we also have this additional condition that the strong energy condition holds for a small time. We also need that the initial extrinsic curvature satisfies this condition. So I didn't show you the function for n because it's a quite complicated function, but the n is a function of those parameters. So of the mass of the field, the maximum field value, the support of the smearing function, how long the strong energy condition is to hold, and when the singularity is formed. The third condition is the existence of a Cauchy surface, and with these three conditions, we're able to prove that the space-time is geodesically incomplete. So this is a theorem where the condition is actually derived from a quantum field theory for a quantum field, and we're able to prove a singularity theorem. Now we go to the third part. Can we apply this theorem to some physical situation and calculate what is this K and if it's a reasonable K? And the application, which is a cosmological application. So we want to estimate this required initial contraction nu that depends on these 5 parameters. We have the mass of the field, maximum magnitude, the time scale for the valid Minkowski quantum inequality, the support of the function. We have the total time scale for the singularity, and the tau naught, the time scale that the strong energy condition is assumed. So first of all, we pick 3 elementary particles with 3 different masses in order to estimate the mass. Logical space-time, but we pick KMS states in order to actually evaluate the phi max, how much the field value can go. And the idea is to calculate this phi max for this KMS state in order to connect that to a temperature. And say the following: if the temperature gets very, very large, our theorem doesn't hold anymore. And then we go above that limit of what is the maximum field value. So this might not be the perfect way to calculate it, but I think it's a nice way to connect it cosmologically, because we know that at early times in the universe, the temperature can go very high. And if it goes very high, then we can say that the semi-classical approximation doesn't hold anymore. So connecting the phi max with a temperature, we're able to put a bound on how large the field value can go. So with these calculations, we are left with 3 timescales: the tau, the T naught, and the tau naught. So there are different methods to estimate those. What we picked was, first, we assume that the time scale of the singularity is much, much larger than the curvature scale today. We want the curvature scale to not be very large. And then with this approximation, we find the optimal tau for the singularity. So we find the tau for the smallest required initial contraction. And these are the results. What's actually interesting is that with these 2 assumptions, this nu is valid for a large range of tau naught time. So the curvature scale today, we take it as 10 to the, sorry, this is minus 11 here, 10 to the minus 11, 10 to the minus 10, 10 to the minus 13. So very, very small curvature scale today, which is nice. And the tau, we want it to be larger than the age of the universe. And this is actually true for the pion and the proton. And finally, we calculate the required initial contraction. So what do we compare it with? Here we need a cosmological model. So we use the lambda CDM model and data from Planck. So the data we took from Planck is actually what is the amount of baryonic matter and dark energy today. And the initial contraction on the cosmic surface is actually in cosmology exactly the same with the Hubble parameter at that time. So we have to go a little back in time to the point where the strong energy condition was last satisfied, because today the strong energy condition is actually violated because of the presence of the dark energy. So we have to go a little bit back in time in order to satisfy the strong energy condition. So with these assumptions, we compare the Hubble parameter with the required initial contraction from our theorem. And what we see is that this is actually satisfied for the pion and the proton. It is not satisfied for the Higgs, and we actually also find that it's not satisfied for the Higgs classically. The reason for that is the large mass of the Higgs that also leads to large field values. So this is still not satisfied for the Higgs. But we still found as required from cosmological observations. So are there any questions before I move to the null geodesics? All right, so for null geodesics, the first thing we need is a null quantum energy inequality. As we had for the time-like ones, we had the quantum energy inequality. So an energy inequality for the null energy, the star-center contracted with null vectors, was derived by Pfister and Raumann in 2002. But you see here that this is averaged over a time-like geodesic instead of a null geodesic. Otherwise, it looks very, very similar with the quantum inequality that I showed you for the energy density. So can we have the same quantum inequality over a null geodesic? So instead of integrating over a time-like path, integrate over a null geodesic? Well, the answer is unfortunately no. And why is because we have a counterexample. So to prove a quantum inequality, you can prove it for a general class of states, but if you find one state that violates it, then the bound is not valid. So in the same work, Pfister and Raumann considered a particular state. This was a sequence of vacuum plus 2 particle states. And then what happens is they allowed the momenta of the state to get very large and become more and more parallel to that null finite lower bound for that quantity integrated over the null geodesic. So this has posed a problem since for having quantum inequalities over null geodesics. What is an idea is to actually put a cutoff to this momenta that cause the problem for the bound. So in QFT, there's often an ultraviolet cutoff, which restricts the 3 momenta. And this is usually connected with the G Newton with the following inequality, less than the UV cutoff, and N is the number of fields. So that led my collaborators in a few years ago to suggest the smeared null energy condition. So this is again a pretty similar form with a time-like one. This is integrated over a null geodesic here. We have one derivative instead of two in order for the expression to be invariant under affine parameterization. And it also depends on the G Newton. So in the G Newton is hidden this UV cutoff. So this bound depends on the UV cutoff of the theorem. But if we have a finite cutoff, we have a finite bound. So the B here is an undefined number, but it can also be a very small number because the largest value the B can take is 1, and that happens when we saturate this inequality. We saturate this inequality when the theorem is very close to the Planck scale. So when the situations where the theory is far from the Planck scale, we can consider that the B is actually a small number. So the SNEC has been shown to satisfy the Fuster-Raman counterexample. So by having this UV cutoff to be finite, we also circumvent the problem of the three momenta becoming very large. And there's a proof of it for free fields in Minkowski space. However, there are also some disadvantages. This bound is not valid for curved spacetimes, and there's not obvious way to generalize the proof for curved spacetimes. It's not also valid for interacting fields. And of course, if we take the UV cutoff to 0, the bound diverges as expected. We can use the SNEC as an energy condition for a singularity theorem in a pretty straightforward way. We can use the semi-classical Einstein equation to bring the SNEC bound to a curvature bound. And then we have the exact form that we need for the theorem. We just have one term, the smearing function with one derivative. And this is the exact same form as the theorem that I showed you for null geodesic. So we can apply the theorem immediately. So here, of course, you might complain that this is, in this situation, we have not taken into account the curvature, and this is true. This is a much weaker theorem that I showed you, the one I showed you for time-like geodesic. So this is valid only for Minkowski space. And the only thing you can say is that maybe this is the dominant term in also in curved space. Of black holes and see what the theorem predicts in that case. So in this toy model, we assume that the metric is approximated by Schwarzschild geometry near the horizon. And so we know the mean normal curvature of the spherically symmetric hypersurfaces in Schwarzschild. So what's the plan is to compare the Schwarzschild mean normal curvature with the required H from the theorem. So in this theorem, the H would depend on the Q1 that comes from our energy condition, the L naught, and the L. The L is the time where the affine parameter where the singularity is formed. Again, we have the two scenarios: the NEC obeyed for the small time, or the NEC violated a little before we measure the mean normal curvature. And this is the scenario I'm going to show you. In this case, from affine parameter minus L naught to 0, we have a violation of the NEC, which I think is an interesting case because in evaporating black holes, we assume that we have some violation of the null energy condition near the horizon. So this is a schematic representation of what we have. The solid circle is the classical horizon. So now, because we need mean normal curvature less than 0, we have to go a little bit inside the black hole. So the dotted circle is the surface that we are interested in. And that surface is inside the classical horizon. So the L naught is the distance from that surface to the classical horizon and where we would require the NEC to be violated. And L is the distance no knowledge where the singularity appears. And these were the results. So, so here, X is giving us the time where the affine parameter where the NEC is violated, and Y is giving us the affine parameter for the formation of the singularity. So what we're interested in is how far inside the black hole we need to go to prove geodesic incompleteness. Ideally, we want to be very close to the classical horizon. But we see that we can't do that if the Q1 is equal to 1 or B very close to 1. So in that case, we have to go at least 1/3 of the Schwarzschild radius inside the classical horizon to prove incompleteness, which is quite different from the classical result. However, if this constant is 1 order of magnitude less, we can go much, much closer to the classical horizon. So to connect that with the energy condition, if our theory is far from the Planck scale, then we can prove a singularity theorem very close to the classical horizon. If the theory is very close to the Planck scale, then we have to go very far inside the black hole in order to prove that. We can do a little better than the smeared null energy condition. And this is some recent work that we're doing. So instead of having a UV cutoff, which has a lot of disadvantages, instead geodesic, but it's an integral over an area. And with this integral, so this is again for Minkowski spacetime, we have a bound that actually looks quite similar with what we had. So we have the G plus and the G minus that depends on X plus and the X minus. We're again in even space-time dimensions. So this is just the number of derivatives for space-time dimensions is equal to 2. And we just have some exponents here. But it is a bound that only depends on the smearing function and the derivatives. And here there is no dependence on any UV cutoff or the theory. So this bound is proven from a general quantum inequality. It can actually be generalized to curved spacetime. So this is the main advantage of this bound. We didn't actually calculate the curvature, but there is a clear path on how to incorporate curvature in this bound, unlike the SNEC bound. And the smearing can be controlled and does not depend on the theorem. We can control how far we're smearing in each direction, and there's no artificial UV cutoff in this case. So this would be a very nice bound to use in a singularity theorem. However, there is a big problem. The singularity theorems require energy conditions that are along only a single geodesic. So we cannot use straightforwardly a bound that is over an area for a singularity theorem. We have recently made a little bit of progress on that, unfortunately only for time-like case, but the results are promising for the time-like case at least. So this is some work in progress, but what we're looking with collaborators is the segment is what we call a segment. Instead of having an energy condition integrating over a single geodesic, we have an energy condition that is integrated over a space-time volume. So we start from a space-time volume along with a weak point-wise energy condition. So this kappa can be very large. And from that condition, the world volume condition, we can prove a condition on a single geodesic. So we can start from our theory with a world volume condition that perhaps has certain advantages, and we can get a condition that is over a single geodesic. And that condition can be used for a singularity theorem. So for the time-like case, the results are very promising. For the null case, which is more interesting, this is still a work in progress. But perhaps there is a way to use this double smeared null energy condition to prove a bound on a single null geodesic. So that's what I had to say. This is some conclusions. For the time-like geodesics, we have a semiclassical singularity theorem for the minimally coupled massive scalar. We approximated the curvature using the partition of unity. What would be better was to prove a new quantum inequality which does not depend on a reference state, but instead renormalizing by subtracting curvature terms, and then we'll be able to directly calculate the curvature. For the null geodesics, things are a little harder. I showed you the smear null energy condition, which uses a UV cutoff, and I motivated its use a little bit and proved this singularity theorem for null geodesics. What would be next? I would say that so far from this work that I've done, it looks like that semi-classically singularities are predicted, and we can prove singularity theorems with quantum fields in a semi-classical context. Of course, this is not a complete work, especially in the null case, but some examples in cosmology and black holes so that this could be possible. Then maybe for singularity resolutions, we would have to look for a full theory of quantum gravity. Thank you.
Very nice. Thank you, Eleni.
Thank you, Eleni, for this very nice talk. Are there any questions from the people? Yes, Tassos.
I have another question. Why do you think that the energy conditions hold for free matter, scalars, for example, and not for interacting? What is your physical understanding for that?
Yeah, that is a good question, because I didn't tell you anything about interacting fields, and there's a reason for that. So quantum inequalities have almost exclusively been proven for free fields. And I mean, the reason is the form of the stress tensor. So for free fields, we can easily express the stress tensor explicitly and quantize it, and then derive bounds for that. Interacting theories, we don't really know how to do that. So the only explicit example I know is in 2 dimensions, and is the Ising model, and there's a quantum inequality for that. But in general, it is very, very hard to prove that. The other thing that I actually heard in a talk a few days ago was also for 2 dimensions, and it was some integrable models. There's also some results for quantum inequalities there. But I don't know of any examples in 4 dimensions, and it's something I'm very interested in. But it's a pretty hard problem because we don't really know how to express the energy density explicitly for these models and derive the quantum inequality.
Well, okay, I was thinking there are many known models in many dimensions. For example, in 4 dimensions, which one could study, say, perturbatively, so that it's their energy momentum tensor is perturbatively close to the free energy momentum tensor. So it maybe that means that there is a kind of perturbative singularity theorem which holds when this perturbation away from the free field theory goes to 0. I don't know how that would work, but would you think that this interaction, so it means that the interaction gives rise to singularities somehow, or to black holes, whereas free fields do not form black holes, do not form singularities?
I think it's a promising path to look future plans to look at those. And I think probably some quantum inequalities hold in that sense, in a perturbative sense. The second case, no, I don't think so. I mean, this work was all for free fields, and I think what it shows is that because there are bounds on how negative the energy can be, we can prove singularity theorems for that. So I don't think in general we need interactions to prove singularities.
And if I may ask another question, what about 3 dimensions, 2 plus 1? Because at some point you mentioned the parameter which is half of the dimension.
Yeah. So these results are for even dimensions, but it is mainly a technical reason, and it mostly has to do with going to Fourier space, for example, and having half the number of dimensions. So I think one could prove things for odd dimensions. So I think for the strong energy condition, it could be a problem to have 3 dimensions. You probably need to go to more, but for other cases, it's not a problem. So for example, for the double smear null energy condition that I showed you, we also have results for, this is for even dimensions, but we also have results for odd dimensions starting from 3. So this could be valid. We don't have a singularity theorem for that, but I think it's possible.
That, I mean, the reason I'm asking is because of a possible relation to holography. You know, you can study 4-dimensional theories, dual to 3-dimensional QFTs. Do you have an idea
but I do have some colleagues here that are doing holography, and but we have just discussed that we haven't made any progress. I think it's an interesting question, and well, it relates also on proving energy condition for CFTs, for example, and then which I think would be easier than proving for general interacting theories. But if you can prove an energy condition for a CFT, let's say on the boundary, maybe you can translate it to an energy condition in the bulk. I think that would be an interesting extension of that. But yeah, I don't have anything more at this point.
Okay, the last, not question, but remark is that with Chris Fuster, we were 1 year apart in Cambridge, so it reminded me of my old days there. So say hello if you see him.
I think I'll probably see him next week. We still work together.
Okay, say hello. Yes,
I will.
thank you. Nice talk, very nice talk.
Thank you.
Okay, so are there more questions from the audience? Then if not, let us thank our speaker again for this very nice talk.
Thank you.
Thank you. And now I'm going to
Thank
stop
you.
recording, and then we can discuss more relaxed, I guess.